Hello, am I audible? Hello, am I audible? If oh, okay, if I'm audible, then we'll wait a few more seconds before we start. Uh, it's 7:01 right now, so I'll wait a few more seconds and then we'll start. Okay. Okay. It's it's 7:05 right now, and I guess we'll begin with our presentation for the day. So, hello and welcome. This will be the first DSC HIT ExploreML presentation for this session. My name is Yashashvi Chakrabarti. I'm a second year CSC student at HIT. And before we begin, let me tell you what ExploreML is. ExploreML is a program that's developed by Google to provide quality content, machine learning education to the masses. So how it works is they provide us with the content like the presentations and the video links, and we in turn provide the same thing to you guys. Uh, One of the students from every DSC college is selected, and they go through a training procedure where they're taught about machine learning and how to teach this course, uh, and that way uh, we come here and then we teach it to you guys. Okay. So before we can begin, actually, I almost forgot. Before we can begin, I'm sending an attendance form on the chat. uh, Please fill this up, because as Shubham said, we might have some swags for later. So if you can just please fill this up. We need to keep a count of how many of you are attending actually. After this, I'll be sending out a post workshop survey. That is not for us. We don't need that, but Google makes it mandatory that all of you attending the session must fill up the post workshop survey so that we can understand how we can make this program better and reach more people. Okay. So yeah, you do that, and without further ado, we'll start with the session. So introduction to machine learning, ExploreML. I know it's kind of redundant that we are doing an introduction to ML again, but since we're trying to bring the intro to ML course of DSC under the umbrella of introduction, under the umbrella of ExploreML, so we're trying to do this the right way this time. Okay.
At tasks through experience is part of being human. When we're born, we know almost nothing and can do almost nothing for ourselves. But soon, we're learning and becoming more capable every day. But did you know that computers can do the same? Machine learning brings together statistics and computer science to enable computers to learn how to do a given task without being programmed to do so. Just as your brain uses experience to improve at a task, so can computers. Say you need a computer that can tell the difference between a picture of a dog and a picture of a cat. You could begin by feeding it images and telling it, this one's a dog, that one's a cat. A computer programmed to learn will seek statistical patterns within the data that will enable it to recognize a cat or a dog in the future. It might figure out on its own that cats have shorter noses and that dogs come in a larger variety of sizes, and then represent that information numerically, organizing it in space. But, crucially, it's the computer, not the programmer, that identifies those patterns and establishes the algorithm by which future data will be sorted. One example of a simple yet highly effective algorithm is to find the optimal line separating cats from dogs. When the computer sees a new picture, it checks which side of the line it falls on and then says either cat or dog. But of course, there can be mistakes. The more data the computer receives, the more finely tuned its algorithm becomes, and the more accurate it can be in its predictions. Machine learning is already widely applied. It's the technology behind facial recognition, text and speech recognition, spam filters on your inbox, online shopping or viewing recommendations, credit card fraud detection, and so much more. At the University of Oxford, machine learning researchers are combining statistics and computer science to build algorithms that can solve more complex problems more efficiently, using less computing power. From medical diagnoses to social media, the potential of machine learning to transform our world is truly mind-blowing. To find out more about machine learning, visit oxfordsparks.ox.ac.uk.
So guys, was that audible? Okay, cool. It is audible. Then, so as you saw in that video, machine learning is, in a sense, trying to teach a machine to learn like a human being. Now, it's not perfectly possible for a machine to learn exactly like a human being. So we try to use statistics to kind of model how human beings learn throughout the time. Okay. So next on, they've asked us to do a small exercise on what machine learning can do. Actually, I did this in a previous session, but let's do this again. So this is called Quickdraw. This is one of Google's open sourced uh, pro- projects of using machine learning in a fun way. What it does is it's like Pictionary, but you're playing with the machine. So it's asking me to draw a leaf.
I see garden hose, or boomerang, or rainbow, or tooth. I see knee, or helmet, or popsicle, or floor lamp, or flamingo. I see parachute, or microphone, or stop sign, or tennis racket.
So
Sorry, I couldn't guess it.
I couldn't get it, but see how every time I draw something, it's predicting in real time. So now it's television.
I see pillow, or keyboard, or postcard, or eraser. I see pool, or microwave, or pencil, or envelope. I see marker, or diving board, or picture frame, or shoe. Sorry, I couldn't guess it.
No,
I see pool,
not
or
even that.
hockey puck.
How do
I see circle. I see donut, or potato. Oh, I know, it's face.
Yeah. So that's how they have applied machine learning in the real world in a very simple thing. For a very simple thing. You can try this out for yourself. You can just go to this link g.co/quickdraw and you can try this out for yourself. So let us first get into the discussion that how does this quick draw game work? Uh, how is it recognizing your drawings, and how can we program this? First of all, since this is about machine learning, we all know the answer to the first question: how does the game work? The game works using a machine learning algorithm. But the question is, can we program this? Like, can we hard code this with proper if and else statements? Is it possible to do that? Well, theoretically, yes, it is possible. You can hard code a quick draw game, but then you'd have to give it every instance of every possible drawing. Like the way you draw a leaf and the way I draw a leaf are very different from each other. So are very different from each other. Hence, uh, just a second. Oh, okay, sorry about that. So we can't really program this in the real world, right? It's gonna be messy. It's gonna be like millions and millions of if and then statements clapped on one after another, and it's not possible for a human being to get every instance. So hence we use something called machine learning. How does machine learning work in Quickdraw? Well, what we do is we send a bunch of pictures of carrots, hand-drawn carrots, its way, differently, and labeled pictures of carrots, its way, one by one, and it learns the features of what a carrot should look like. Like, if I gave you any of these pictures, you may know that it's a carrot, but for a machine, it's really, really hard to understand. Because for us, it's pretty simple because we've been taught to learn that way since we were children. But for a machine, this elementary task seems very difficult. Hence, machine learning. So for a rule-based approach, what we do is we frame the goal of the product. Designers or engineers develop flow and logic, and we refine until goals are met. So if object height is greater than 10, do X. If object dot color is blue, we do Y. If object dot number of legs is greater than 2, we do Z. So you understand how many if and else statements we have to program at every level for every particular picture. I need to program how A draws a carrot. I need to program how B draws a carrot. I need to program how C draws a carrot, right? So this becomes very tedious. Hence, the next answer is machine learning. We frame the goal of the product. We train a model using examples like different kinds of hand-drawn carrots, and we refine until we meet the goals. So what refine means, we train a model to reduce the loss as much as possible. Like whenever we draw a different kind of carrot, the algorithm should understand that it's a carrot. So we keep on refining until we get the right answer. So here's an example of how you can think about machine learning. So which approach should you use for alphabetizing a list of song titles? Is it a rule-based approach or a machine learning approach? I'll give you a few seconds here. I kind of feel like Dora the Explorer, if you remember. Like she would stop in the middle of a show and start asking questions. There would be long awkward pauses. We wanted to do this in real life, but since the college hours didn't allow it, so here we are doing it on a webinar. So alphabetizing a list of song titles. Well, it's a rule-based approach, obviously, because if the first alphabet or the preceding alphabets, according to the rank, are come before the other, we can simply make it a rule-based approach. We don't need machine learning for this. Ranking web search results. Now this is interesting, right? Traditionally, web search results have been always ranked on a rule-based approach. They've been hand-coded. There have been hand-coded algorithms that say which search comes before which. But in recent times, we've seen that machine learning can do that a lot faster and a lot better than us. Why? Because ranking a web search result depends on several different features. It's not just how many times someone goes to the page and the how correlated the search words are. There are hundreds of different features that Google needs to take into account, or any web search engine needs to take account before they can create a web search ranking result. So here it's both rule-based and machine learning. Wait, are there any questions right now? I just need to check. Okay, cool. Someone's pissed at my drawing skills. Anywho, so this is rule-based. Next on, prediction of house prices based on location. This is actually a real data set, the California housing data set. If you go to Kaggle, or if you go to Google Colab, you'll see these data sets exist. So it gives you the number of houses in a housing complex and the area, location, the square footage, and based on that, you predict the prices. So predicting housing prices, it's obviously machine learning, because there are so many features and so many different things to look into before you can't really build a rule-based approach to this. Processing online payments. Here it's rule-based. Why is it rule-based? Because processing online payments, there can be no ambiguity. Like a machine learning algorithm ranks things very well, but there is always an ambiguity of where it will put a certain kind of a certain element. But here you don't want that. You don't want to harass potential customers saying their transactions look kind of dicey to a machine learning algorithm. You need to have a proper rule-based algorithm so that it can check. Classifying an object in the photo, this is quite obvious. This is very obvious. Obviously, it's machine learning. That's basically why we invented neural networks, so that we can classify pictures and objects in pictures. So a recap, a rule-based approach, rules are properly defined by human beings. Those are usually if and else statements or loops and that kind of stuff. And over the time, we improve algorithms and the network so that we can reach somewhere near our goals. But in machine learning, there are no rules defined by human beings. At best, we can choose what kind of algorithm fits this kind of problem. But after that, there is really not much we can do except for wait for it to train, learn from the patterns, and then later, after it's learned all everything and we've tested it, we can then think of improvements of changing the algorithms or adding additional data or data augmentation. There's a lot of things you can do, and that way we can improve the algorithm. Each has its benefits, obviously. If one was better than the other, then we wouldn't need the other, right? So each has its benefits and each has its place, but here we'll mostly talk about machine learning.
Suppose you have a great business idea and you've already gone through the effort to frame it as a machine learning problem. What next? How does your idea become a working machine learning solution? The process has 3 phases: data, modeling, and production. In the data phase, you identify the input data that your machine learning system needs to make successful predictions. Data may come from databases, log files, web pages, and even other machine learning systems. Once you identify data inputs and sources, you use statistical tools to draw insights about the data. The better you know your data, the more useful hypotheses you can make. Data rarely comes in an ideal state. Data needs to be collated, possibly by joining different data sources, and cleaned for the machine learning model to work optimally. Cleaner data results in better predictions. For a machine learning problem, you start with the input data and convert it into features. Features are key properties of the data. For a supervised machine learning problem, you transform the outcome into labels. Labels represent the intended output of the machine learning system. Joining data sources, cleaning the data, and engineering the features and labels takes time. Plan on spending a large portion of your time in the data phase. Modeling phase. Along with the features and labels, you set up the kind of machine learning system needed, called the model. Researchers have created all sorts of machine learning models, from simple to complex. Some models classify data. Other models predict numeric values. Tools like Google's TensorFlow support many types of machine learning models for various uses. Before a model can make predictions, it needs training, which is like sending the model to school. First, there are lessons to learn from the data. Along the way, there are quizzes to check knowledge and correct any misunderstandings. In the end, there's a final exam. When training the model, you split the data into 3 sets: training, validation, and test. The training set corresponds to lessons. Here, the model processes data for the first time. It starts to infer patterns in the data to help make predictions. After you've trained the model once, you quiz it using the validation set. Based on how well the model does on the quiz, you may decide to adjust the model settings, or hyperparameters, which are like dials and switches for changing the model's behavior, and retrain the model again to give it the quiz again. The goal is to iteratively find settings that provide the best model quality on the validation set. When the model meets your success criteria, it's time for the final exam. Feed your model the test set. If the model predicts well, it passes the course and is ready for real use. Once your ML system is ready for the world, it's time to move the system into production. For starters, your system may need integration into a product. You need to figure out what this integration looks like,
and whether your model interacts with users. Models may need retraining on a regular basis with new data to pick up on new patterns or trends. This training could come from new data sets or from interactions with users. The system needs monitoring. This means tracking system outages, errors, data processing volume and speed, and how successfully it predicts results. Machine learning systems also require maintenance. As with any production system, this means fixing bugs, adding features that didn't make it into version 1, and the like. Machine learning specific maintenance could include testing other models and settings to see if performance improves.
So this explained the entire machine learning development workflow. The most important takeaways aren't the production part, because that we come to later, and usually it's not the duty of the machine learning engineer to understand how production will work. The most important part, or the things that I want you to take away from this video, are the test, train, and validation sets. Now, in multiple machine learning interviews and even in the machine learning communities, there is always a kind of debate about what validation actually does or what test actually does. But the way they've explained it here is very simple. So training data is your lessons. You go to the college, you learn something. That's your training data that your teachers give it to you. Validation is self-evaluation, kind of. Like with validation, you can iteratively change the process. If you learn something, you test it on a validation set. If you do well, great. If you don't do well, then you change your hyperparameters or your learning parameters in such a way that you can better take the validation test next time. And after that, once you're done with that, you can't change your hyperparameters once you've tested on the testing data set, right? That is the kind of a benchmark for your algorithm. So if it does well on a testing data set, then you can say, well, my algorithm has so and so percent prediction probability, or so and so percent of loss. If you can't say that about in the validation set, because the algorithm is in some ways seeing the validation set, but the testing set, the algorithm has never seen the testing set. Hence, we can call it for a benchmark, right? So next up, yeah, this is kind of a mind map to explain the machine learning process. You first define your objectives. Focus on the user. Yeah, sure. That should be the first step. But let's get real right now. You define your objective. You define your problem statement. You understand what things you'll need to go forward. And you need to understand if at this point in your journey, you're capable of something like that. This is very important, because if you start training models, extremely complex models with huge number of hidden layers in a deep neural network, you might be able to get some viable results, but that's no use to you because you don't understand how it actually works. So you need to be aware of your capabilities before you get into a machine learning project. If you want to train a robot with reinforcement learning or something, you first need to understand how neural networks work. So understand your capabilities and slowly take the steps towards it. Then you collect data, you train the model, you test the model, and then you predict. If evaluation is good, then this goes into production. If it's bad, you go back to collection of data, you change the data somehow, you need to clean it or something, and then you do this all over again.
Let's play a game. Close your eyes and picture a shoe. Okay, did anyone picture this? This? How about this? We may not even know why,
But each of us is biased toward one shoe over the others. Now imagine that you're trying to teach a computer to recognize a shoe. You may end up exposing it to your own bias. That's how bias happens in machine learning. But first, what is machine learning? Well, it's used in a lot of technology we use today. Machine learning helps us get from place to place, gives us suggestions, translates stuff, even understands what you say to it. How does it work? With traditional programming, people hand code the solution to a problem, step by step. With machine learning, computers learn the solution by finding patterns in data. So it's easy to think there's no human bias in that. But just because something is based on data doesn't automatically make it neutral. Even with good intentions, it's impossible to separate ourselves from our own human biases. So our human biases become part of the technology we create in many different ways. There's interaction bias, like this recent game where people were asked to draw shoes for the computer. Most people drew ones like this. So as more people interacted with the game, the computer didn't even recognize these. Latent bias. For example, if you were training a computer on what a physicist looks like, and you're using pictures of past physicists, your algorithm will end up with a latent bias, skewing towards men. And selection bias. Say you're training a model to recognize faces. Whether you grab images from the internet or your own photo library, are you making sure to select photos that represent everyone? Since some of our most advanced products use machine learning, we've been working to prevent that technology from perpetuating negative human bias. From tackling offensive or clearly misleading information from appearing at the top of your search results page, to adding a feedback tool on the search bar so people can flag hateful or inappropriate autocomplete suggestions. It's a complex issue and there's no magic bullet, but it starts with all of us being aware of it so we can all be part of the conversation. Because technology should work for everyone.
So that was human bias, how bias is introduced to a model. This is all very high level stuff where you want to clean your data sets and that kind of stuff. We'll get into the nitty gritty later. But for now, just understand what bias is. We'll later tell you how to tackle bias. Like there are ways you can do that. You need to be aware of your data first and foremost, but that'll be for some other time. Today we'll just talk about this introduction to ML, and we'll give a brief introduction to neural networks. So please stay till the end of the presentation because neural nets are important. That will be the most important part of this presentation today. So what can ML do? Well, what the real question should be, what can't ML do currently? But well, most of the things that look elementary to us, to a computer, that's very difficult. Like a computer can understand how the world works, the galaxy, the universe works, how the Earth revolves around the sun, how the Milky Way galaxy revolves around in the universe. It can model it very well, but it can't predict whether an image is a cat or a dog. That's very difficult for a machine. So that's where machine learning comes. And these kind of tasks where a traditional machine traditional programming approaches failed, we used machine learning to solve those problems. So this is kind of a Venn diagram of machine learning. It's artificial intelligence, that's then machine learning. This is really common knowledge right now. So machine learning is a kind of stuff that you need to work on big data, on algorithms, on technology. So I really don't know why they've provided this kind of Venn diagram, but fine. So there are different kinds of machine learning algorithms. The most common ones are called classification algorithms, where you look at a picture and you try to classify it into a category. This category could be like here it's shown a lion could be a mammal, a wildlife, or just simply a lion. So that's classification problems where you try to differentiate different kinds of data points. Next is regression. You need regression when you need to predict something that's new. So say I have the stock prices of a particular company from 2010 to 2019, and I want to predict what its stock price would be in 2020. So here the regression comes in. Now, a lot of you who have studied regression in your second year might ask, well, I can do that on pen and paper. Like, I really don't need a machine learning algorithm for this. True, you can do two-dimensional regressions quite easily, and if you can even do it on higher order polynomials like a parabola or something like that. But for higher dimension regressions, like a machine can handle hundreds of dimensions at the same time. You can't do that on pen and paper, or even like you can't do that with a calculator. You need a machine learning algorithm to slowly keep testing and keep increasing dimensionality. That's how regression works. Clustering. So we talked about this in the last presentation. Clustering refers to joining similar kinds of data types together. How it's different from classification is, in clustering, it's usually unlabeled data. The machine does not know what it's trying to predict or what it's trying to differentiate. It just clusters different kind of data points differently and then spits out an output. This is very helpful for ATM fraud detection or account spam filtering, these kind of stuff where the machine does not know what it's looking for, but it can see what data point is an irregularity in the data space. Again, clustering is easy in two-dimensional for human beings, but in higher dimensions, human beings fail at clustering. Sequence predictions. We use something called a recurrent neural network where to predict sequences. I know it's a big word and kind of a mumbo jumbo for you right now, but a computer can predict what comes next in a sequence. Like if you feed it a few prose of Shakespeare, it will try to predict what the next word should be. That's how sequence prediction works. Style transfer. Actually, style transfer is a bit more complicated, and you need to understand how neural networks work and how they extract features from pictures to understand how style transfer works. But simply put, style transfer refers to the kind of algorithms that take a certain image and map it on a certain different image. Like here, we're we're mapping this turtle image on this picture of on this painting of waves, and we get a result that somewhat looks like this. You might have used these kind of stuff in your more filters on your cameras, where they kind of put something else like like a Picasso painting of your face, something like that. That's style transfer. So again, a kind of quiz. Type of machine learning, recommending what someone will download based on previous purchases. Is it classification, clustering, regression, sequence prediction, or style transfer? Think about it for a while. It's sequence prediction. So probably Amazon or Flipkart uses an algorithm like this, where after every purchase, a sequence of your purchases is built, a data set of your purchases is built, and next after that, it kind of tries to predict what you'll need. Like probably after the purchase of something like hot sauce or something, it will predict that you'll need a toilet paper next, something like that. Labeling email as spam as not spam. Here they have used classification, but usually this problem is solved with clustering. But yeah, you can do this with classification too. Identifying trends amongst a group of people who have bought a new music release. Well, that's clustering, because it's not necessary that each and every one of them have bought the same release, but similar kinds of releases are clustered together, and hence you create a data set of, say, metal fans, or rock and roll fans, or pop fans, or K-pop fans. Captioning a video, style transfer. Determining workout activity based on phone movement, classification. Like, what kind of workout do you do on based on phone movement? If your phone bounces up and down every few seconds, that means you're running. If it changes changes on one axis, that means you're doing crunches or something. That's classification. Identifying famous landmarks in a photo, that's classification. Suggesting spelling errors, that's clustering. So there are a few other of this, but I'll come to the end of this. So to wrap up the first part of this session, we have a few review questions. What is machine learning? Well, machine learning refers to development of algorithms so that we can teach a computer like a human being. We've covered machine learning versus rule-based approach, and we've kind of dealt with what AI versus ML versus deep learning is. We'll further understand what deep learning is when we get into neural networks, and we've done types of machine learning. So any questions thus far? So someone asked how unsupervised regression is used in self-driving cars. I really don't know the answer to that right now, but I will get back to you on this. Unsupervised regression. See, whatever algorithm you used for driving for self-driving cars needs to be unsupervised. You can't go on labeling everything in the world that a car would face and label that as obstacle or not. The car needs to understand whether a certain thing is an obstacle or it's just something you pass by, right? So I guess that clears the unsupervised part, but the regression part I'm really not sure about, but I'll get back to you on that. With that, we come to the more important part of the beginner track in machine learning. That's neural networks. Neural networks are the building blocks of deep learning, which is one of the most studied and researched part of machine learning today. So before I start explaining what neural networks are, let me put a video on.
Hi, I'm Nat. And I'm Lo. And this is our 20% project, where we go find out about different Google stuff we're curious about.
Last year, we got to make a documentary about how voice search works. And that was the first time we heard about something called machine learning.
Since then, we've been kind of fascinated by it.
So today we're talking with Greg and Chris to learn more about it. How would you describe machine learning to someone?
Well, there's a lot of problems that's really easy to solve with computers. Computers can go and simulate how galaxies move and how the courses of asteroids going and how close they're going to come to Earth. I could never hope to go and do that, but I can go and do this problem like recognizing that that's a tree, which is so much tremendously more difficult for a computer.
It doesn't feel like intelligence to us because it's so effortless as a human being to do it, but for a computer, it's actually really hard.
Because the real world is kind of messy and unpredictable at times. The strict logical rules that go into traditional programming just don't work.
Instead of going and writing programs that solve the problem, we write programs that learn to solve the problem from examples.
And it's this process of learning that allows them to improve over time and to actually be more clever than they would be if we wrote down a very rigid set of instructions for them to follow.
Machine learning is in so many different things that we use today that it's kind of like this invisible magic ingredient.
Phones with the ability to understand human speech.
Machine translation, email spam filters.
When you go to the ATM and you give a check and it can read the handwriting.
or a Photos app that can automatically organize your photos based on the things that you like to take photos of. Like, here are all my mountain photos, here are all my food photos,
Here are all my dog photos.
here are all my feet photos.
Everything from facial recognition to going and trying to recognize whether a particle is present in a particular collision at the LHC.
Which we just like to take a time out to say is that big tube in the ground over in Europe that smashes particles together at really fast speeds so that scientists can use that information to unlock the mysteries of the universe, among other cool things. Now back to our episode, because I am getting really dizzy doing this. Ooh, ooh.
So researchers and scientists are still experimenting and trying to find the best ways to teach computers how to learn. But a lot of the progress is coming from these algorithms that are based roughly on how the human brain works, and these are called artificial neural networks.
So an artificial neural network is something that it's a rough mathematical cartoon of how a biological neural network works. In a biological brain, we have individual cells called neurons. Each neuron looks at what its neighbors has to say and then decide what it wants to say. And in artificial neural networks, we have little mathematical functions. We put them in some organized structure, and then we say, okay, you guys all together, learn to do this task.
We have lots of neural nets that are really great at going and recognizing, this is a cat, this is a dog, this is a frog, this is a mouse, this is a horse, this is a truck, and things like that.
So take, for example, trying to recognize what this is.
So it used to be that we were really proud if we could get a neural net with 3 layers to work. And it's recently that we've made a lot of progress on techniques that allow us to train much deeper neural nets.
And that's why this kind of machine learning is also called deep learning. A neuron in the bottom layer is just going to be looking at a tiny piece of the picture and making some computations about it. It doesn't understand anything about dogs specifically.
But what the neuron does understand is it says, I'm giving a signal that's useful for somebody who's giving a signal, who's giving a signal, who's giving a signal, who's giving a signal.
They're kind of able to unfurl this really high-dimensional knot and pull it apart and make it easier to go and separate different things that are close together on the surface from things that were tangled all together earlier.
But then at the top, we'll put 2 neurons, and these neurons look at the whole picture so far.
They're basically experts at making the final call, figuring out, oh, all the layers below me said these things, so I know that this is a dog, or at least I'm 92.4% sure that it's a dog, so it's basically a dog.
And while there's been a whole lot of progress with teaching computers to learn, they're still much slower learners than we are, and they make mistakes that you and I wouldn't.
So what I was working on is sort of trying to find a way to go and look at a neural net and ask, what does the neural net think the platonic ideal of a cat is, or the platonic ideal of a dog, or anything it can classify as? And suddenly you can go and ask, neural net, what do you think a cat looks like? And you get a picture of a cat, or, neural net, what do you think a barbell looks like? These weights. And it goes and it shows you a picture not only of a barbell, but of an arm attached to a barbell. So the model thought that the arms, it only learned what barbells were from looking at pictures of barbells, and they're often held by muscular weightlifters. And so it learned that there was, barbells have arms attached to them.
It takes them a long time to learn. You show it a picture of a school bus when it's early in learning. The very next time you show it a picture of a school bus, it's only a little bit more likely to say school bus. It doesn't get it, even though that was the very last thing it saw. Whereas, say to a kid, that's a filing cabinet. And then a second later you say, what's that? He's not gonna be like, shoe, right?
Well, like, the more you describe this, the more I'm amazed by human beings.
Yeah.
Like,
yeah.
The effect is like, wow, human beings are really amazing.
We're really amazing learning machines.
Oh. So that's kind of the best way to explain what neural networks are and how do they work. Basically, what happens is when we are talking about in context of a picture, we take the picture and the picture, say, is a black and white one. So we only have values of how black a pixel is. We take that picture, we squish it into a single array. Like it was a matrix of numbers varying from 0 to 255, and we take it and we squish it into a single dimensional array. We take that array and feed it like that's the first input layer of our neural network. That becomes the first input layer of a neural network. Those values go to the next layer after they've done some calculations on it. Say they've multiplied it with some value or divided it with some value, and then it goes to the next level, and then it goes to the next level until the output layer where it predicts based on what values it gets on the last level. That's how neural networks work. So what neural networks come with are something called activation functions. An activation function is, it takes the value of that particular node and then puts it through a function and tells whether this neuron should be active or not. By the way, neurons, when I say neurons, they are the connection between two layers. Those are the neurons. And when I say if it should be active or not, by that I mean, should that have a high value? Should that have a value so that it becomes important in the next step? So activation functions decide whether that particular neuron should have a high value or a low value. To explain you better, say I put 5 through a neuron. Okay, that's my signal. 5 is my signal. In the next stage, in the activation function stage, the activation function checks if 5 is less than 10 or not. Well, yes, it is. Then we say, okay, this neuron is active. Means I let this 5 value pass through the activation function. If we pass it a value of something like a pixelated hand-drawn image of 7, and we say the activation function asks, does that have a curve? Well, 7 clearly doesn't have a curve. Hence, the activation function says no, and we do not activate the neuron. In other words, the neuron passes a very small value or a 0 value, and in the next layers, it's not that valuable anymore, because any multiplication done on 0 remains 0, right? Similarly, does 6 have a curve? Yes, 6 has a curve. Yes, then activation. Some common activation functions are sigmoids and ReLU. ReLU is a rectified linear unit. What sigmoid is, it kind of squishes all the values together. Say, like I said, sometimes images, pixel values come from 0 to 225, and you don't want that large values to pass through. So what you do is you squish them together. You squish them in between 0 and 1. So whatever value you pass through this function, it is squished between 0 and 1. Now, if this node has a very high value, then we'll get a value that's very, very near to 1. Say we have a value that's very close to infinity. That means that should be 1, right? So that the activation function says, okay, you have a very high value, I'll let you pass, and it gives it 1 value. Again, say the same has a very, very low or a negative infinity, tending to negative infinity value, and the activation function, the sigmoid function, sees this and says, well, you're very, very low, and I don't think you will be important in the next layers. So what I'll do is I'll pass you as 0 or very, very near to 0, thereby reducing its importance. ReLU is actually quite a simple function, like you can see from this image. Fx equals to max of 0 and x. That's like stupid easy, right? There's an improvement of this which is called a leaky ReLU, where at the end of the 0 line, near the 0 line, the origin, there is a slight curve. But what it does is, it's basically, if your value is negative, you will be 0. If your value is positive or greater than 0, you will pass the same value as it is. This is very useful for when biases become very negative. When bias is referred to the thing that we are adding to these nodes. So when biases become very negative, what we find is it's very difficult to work with negative values, and neural networks don't really like negative values. So we make everything positive, and only the neural network neural nodes that have a positive value shall be allowed to pass to the next part, and that have a negative value are stopped right there. So this is kind of the high level way of seeing how a neural network works. What it does, it takes the image and say you have a straight flattened array of values varying from 0 to 1. Okay, decimal values varying from 0 to 1. What you do is you take that array and you multiply each of them with a weight. Weight is any number, and that's the thing that we usually train. Um, that's the parameters, the hyperparameters that a video before this was talking about. We train those weights and biases. Bias refers to whatever is added to this. Weight is what we multiply, bias is what we add. This is basically a matrix multiplication where every node is multiplied with a weight and then passed down to the next layer. Say from my input layer, I have 1, 2, 3, 4, 5, 6, 7, 8. 8 input nodes and 4 output nodes. So for my input 1, for the first input, I'll have 4 different weights and 4 different biases. Each of them will be trained in later steps so that the neuron will only be activated if a feature that refers to a Labrador retriever is met. So these weights and biases make sure that our activation functions are working properly, that our activation functions only activate when we really need them to. So this is a very interesting thing that Google allows us to do. It's called a neural network playground exercise. So wait a second. So here they let us use a data structure, a data set, and train it with as many number of neurons as we wanted to. So I can add more neurons, and as you see, as I add newer and newer neurons, I need to classify between what's orange data and what's blue data. So I'll regenerate the data a few times. I'll add newer neurons, and every time I add newer neurons, it tries to find some kind of feature that can be used to differentiate, but it loses every time. So what we do is we need a linear. Wait a second. Here it is. So I'll put this link in the chat. And I guess you guys can play it with it too. So what we have here is we have different kinds of data. We have this kind of circular data where mostly orange spots are on the outside and bluer spots are in the inside. We have very well differentiated data, and we have some spiral data sets. So now to solve our problems, we could either increase the number of neurons, and thereby somewhat a line draws here, right? So we are at 169 epochs. That means we have trained the model 169 times, and yet we can't find a clear distinction between what exactly is there. And you'll see that for the spiral data, where the data is kind of mixed and matched and it's not linear, you can't draw a linear line through it. It's very difficult for a single layer of neurons to solve this problem. See, there is no differentiation. But if I add another hidden layer, it just might. I'm not saying it will, but it just might. So it's slowly trying to differentiate between data. I'll add another layer. And So it's still unable to differentiate between the spiral data. What we do now is we introduce something called feature engineering. We take the x square and x1 square and x2 square, the two axes, as our features, and we train it again. This time without the hidden layers, I guess. This should work. Yeah. See how it kind of learns some way to differentiate between this, and the test loss is decreasing. So it's trying really hard, you can see, but it's unable to. I'll add a few more layers here. So at 233 epochs, we still have test loss at around 0.45%, 0.45, and training loss at 0.323. So I'd ask you guys to play with it as much as you can and try and understand how neural networks work. See, they have given even more features to us. So you can check if these features work and if adding newer layers, hidden layers, actually does what it's supposed to do. Right? So you go through this exercise. I'd ask you to go through this exercise yourself. And if you have any problem with this, you can ask in the group. I've given the link here, and I'll give the link again. Just go through this whole document one by one. This is kind of an exercise that we were supposed to do together, but since we are doing it on a webinar, it's really difficult to interact with you guys. So I'd ask you to do it at your home and try and understand how neural networks work, and how just adding new and new layers doesn't mean your system will work better. There was another part that we needed to do that was called teachable machines. I guess most of you have seen what teachable machines are, because Shubham took teachable machines in some of the classes. But what it basically does is, say you want to train something with, say I want to train it with my with a V sign. So I take a few, I take a few examples here around. Yeah, that's fine, I guess. Then I train the purple one with a fist. And I train this one with a thumbs up, I guess. So I guess every time I make a V sign, it should show the cat. Every time I make a thumbs up, it shows the, what is this? Is it a mouse? It's a mouse. And every time I show the fist, kind of shows the dog. But it's not perfect, right? It can be fooled in a lot of ways. Say I make a fist like this. It's kind of confused between which one to choose. The moment I take my thumb, if I make the fist like this, I don't have a thumbs up, but it's still confused between all of them at once. So this is the way you can confuse a neural network. I'll put the link for this too. And you can play with this. So to review, we learned about what a neural network is. We'll get in depth into neural networks, where I'll show you the math of how they work later on in a live session, in real life session. But for now, you just understand that neural networks are kind of signals from a data set that try to mimic how our brains work, and there are something called activation functions that tell whether a neuron should be active or not based on what kind of features we're looking for. When is it useful? It's only useful when you have a lot of data. Okay, so if you just want to do a simple regression or a classification with say 10 features, say if you want to predict the housing prices, so you have the number of houses, the locality, the square footage, like this, you have say 10 or 15 fields. A neural network won't work very well here because it doesn't work well with fewer feature models. But if you say have hundreds and hundreds of features in a picture, it's usually uh, 28 by 28, so around 700 different features, and you can't train a simple classification model with 700 features. But with neural networks, it's very easy to train 700 feature classification. So you need a lot of data to train neural networks. What can it do that a simpler model might not be able to do? What it can do is it can generate, like, understand features, higher level features that we don't put it into it, right? It will understand what a dog looks like. We are never telling it that a dog has a longer snout, or a dog usually varies more in size than a cat. We are not telling these things. We just show him its data set, a labeled data set, and it's understanding, learning these features layer by layer. Say the first layer, it only learns the structure of a cat or a dog. It's not very helpful because dogs and cats, structure wise, dogs and cats look very similar. But as we go deeper and deeper, it tries to pick out some specific features, such as dogs have longer snouts sometimes, or dogs have different kind of fur colors, and cats are usually smaller, and cats have different ears than dogs. These are higher level features that the model slowly learns as it goes deeper and deeper into the network. And these can't be done with traditional machine learning algorithms, because traditional machine learning algorithms, you define the features and you train them on it. In neural networks, you don't really define the features. You're asking the machine to develop the kind of features that you need. Well, what are the limitations of neural networks? As I said, it doesn't work with very few features. Also, it needs a lot of data to learn, and it's usually slower than most other machine learning algorithms. It requires more compute power. These are the limitations of it. I guess there are a few more, but I'll leave you to discover those as you go through those exercises. So we are open to question now. If anyone has any questions. Someone asked, what is style transfer? Okay, like I said, neural networks extract features from an image and then put it into, and then they learn on the basis of that, right? So what style transfer, or more specifically neural type style transfer, refers to is you extract those features, but you don't predict anything. You extract those features from a particular image, and then you try to map it on a different image, like kind of filters on your phone. If you want a Picasso filter, or if you want a Mona Lisa filter, if you want your face to look like Mona Lisa, what it does, it's a model goes through the Mona Lisa picture. It extracts all kind of all kind of sorry, all kinds of features, and then it maps it on your face. Which type of machine learning? Which type of ML? It will be for stock market emotion analysis. There are a few different ways. Whenever there is a time factor, whenever you need to predict based on time, it's best to use something called recurrent neural networks, which it's like if you've studied feedback amplifiers, it's kind of a neural network that has a feedback loop. So output of the second layer, usually the second layer, goes back into the input as a new uh, neuron, and that way we try to take into account the time. There are no more questions. So if we don't have any more questions, then it's probably time to end. Thank you so much for joining. If there are any more questions, then please leave it in the groups and I'll get to those later. Okay, thanks. Bye.